Imagine you were standing in the middle of a massive field, and surrounding you are, well, just a million hyperactive cats, all running in completely random directions.
Absolute chaos.
Right. Absolute chaos. Now, imagine someone hands you a whistle and says, your job is to get every single one of those cats to line up and perform a perfectly synchronized marching band routine.
Which sounds entirely impossible.
Completely impossible. But that exact scenario, trying to herd the ultimate cosmic cats into a parade, is actually the fundamental struggle that governs everything in the physical universe. So welcome to today's deep dive. We are thrilled you're here with us.
We really are.
Today we have a fascinating stack of handwritten engineering lecture notes covering the fundamental concepts of thermodynamics. And our mission is to basically unpack the basic rule book of reality.
It's a big task.
It is. And for this discussion, think of me as the highly curious student, encountering the underlying logic of these concepts fresh. While sitting across from me is our resident expert, who is going to be our guiding professor today.
I'll do my best.
So to our listener, pull up a chair, lean in, and let's unravel together how energy actually governs everything around you.
It really is a brilliant way to frame it, the cats and the marching band, and I'm looking forward to walking through this with you. What makes these concepts so compelling is that, well, they strip away the intimidating exterior of physics.
Yeah, the scary math.
Exactly, the scary math. And they get right down to the fundamental truths of how reality operates. We're going to look at how we study energy, how we draw boundaries around the things we want to understand, and ultimately the rules that dictate what is and isn't possible in our universe.
Okay, let's unpack this. Because if we look at the pure etymology of thermodynamics, it's actually incredibly revealing. You have thermo, from the Greek word for heat.
Right.
And dynamics, meaning motion. Specifically, motion caused by a force acting on a moving body, which engineers define as work. So heat and motion.
Precisely. And that combination of words directly reveals the grand aim of the entire field. I mean, the primary goal of thermodynamics is to convert a non-organized form of energy, which is heat, into an organized form of energy, which is work.
Which brings us right back to our cats and our marching band.
It really does.
Heat is the chaotic, milling crowd of cats, right?
Mm-hmm.
The molecules are buzzing around randomly, bumping into each other. They're full of energy, but completely lacking any unified direction.
Just kinetic chaos.
Yeah. And work, on the other hand, is the marching band. It's energy moving together in a single useful direction to, push a piston down a cylinder or spin the blades of a turbine.
Thermodynamics is literally the science of herding those molecules into a parade.
That is an incredibly accurate analogy. And what makes thermodynamics unique as a scientific discipline is that its foundational laws aren't derived from complex mathematical proofs.
Wait, really?
No, you cannot prove them mathematically in the way you can prove, like, a geometric theorem. They exist as statements of universal truth based entirely on common human experience.
Oh, well. Yeah, every single time we observe the universe, this is exactly how it behaves.
So it's essentially an empirical science. We just keep testing the universe.
Yeah.
And the universe keeps giving us the exact same boundaries.
Exactly. And because of that, thermodynamics holds a really unique position. It is the only subject that explicitly tells us what is not possible.
Like a physical speed limit or something?
Kind of. For example, the second law of thermodynamics dictates that no heat engine can ever achieve 100% efficiency. It's just a hard physical limit set by reality.
You can never get all the cats to march perfectly.
You can't. Some will always run off into the bushes. You will always lose some of that organized energy back into disorganized heat.
Man, that's a hard thermodynamic tax to pay when you're designing an engine. I mean, we build these incredibly complex machines, power plants, jet engines, refrigeration cycles, and the universe essentially demands a chaos tax off the top.
That's a great way to put it, a chaos tax.
But to even begin designing those machines, to study this marching band of energy, we have to decide how closely we're actually going to look at the molecules.
Yeah.
Right? I imagine classical thermodynamics completely falls apart if we're dealing with something like a satellite in the upper atmosphere.
Oh, absolutely.
Like when molecules are miles apart, you can't just average them out.
You've hit on the crucial distinction between the macroscopic and microscopic viewpoints there. What you just described with the satellite, that's the microscopic view, which relies on statistical thermodynamics.
Right.
When you have highly rarefied gases, or say if you are working in extreme cryogenics, the molecules are so sparse or moving so uniquely that you have to analyze the statistical probabilities of individual molecular behavior.
Because tracking every single collision of trillions of molecules in a standard room would require computing power we just don't even possess.
Exactly. I mean, it's impossible. So for the vast majority of engineering purposes, we use the macroscopic view, classical thermodynamics.
Okay.
We don't look at the individual molecules at all. We fix our attention on a certain quantity of matter and look at the average aggregate behavior of all those molecules combined. It is a much more practical way to study properties like pressure, temperature, and volume.
Right, that makes sense.
But to safely use the macroscopic view, we have to assume something called the continuum.
The continuum being the assumption that the matter we are studying is completely homogeneous, right? Like with absolutely no holes.
Yes, exactly.
We just pretend that a gas or a liquid is a smooth, continuous blob of stuff rather than a bunch of tiny individual atomic dots bouncing around with empty space between them.
That's right. If the continuum assumption is valid, then statistical averaging is highly meaningful and accurate. We can just insert a pressure gauge into a pipe and read a single, stable value.
Instead of trying to calculate the momentary kinetic energy of quadrillions of individual air molecules hitting the sensor.
Exactly. It saves us from impossible math.
I understand why we want to do that, because it makes the math infinitely easier. But, and I have to push back a little here, how do we actually know when we can safely model matter as having no empty space?
It's a very fair question.
Right, because at a certain altitude or a certain low density, that assumption just has to fail. It can't just be a convenient lie we tell ourselves.
It's a vital question, and engineers don't just guess. They have a specific mathematical parameter to verify this called the Knudsen number. It dictates exactly when the continuum assumption is mathematically valid and when it breaks down.
Okay, break that down for me, because I know the Knudsen number relates to the mean free path of a molecule compared to the size of the system, but how does that actually play out in a physical design?
Let's visualize it.
Yeah.
So the mean free path is the average distance a single molecule travels before it collides with another molecule. If you think about walking through a tightly packed concert crowd,
Oh, I see.
how far can you move before you bump into someone?
Not far at all, maybe a few inches.
Right. Your mean free path is very short. Now, the characteristic dimension is simply the physical size of the system you were studying. It could be the diameter of a pipe or the length of a combustion chamber.
Okay.
The Knudsen number is simply the ratio of that mean free path to the characteristic dimension. It asks, how big is the distance between molecular collisions compared to the size of the whole system?
So if I have a highly pressurized gas inside a very large tank, the molecules are crammed together, bumping into each other constantly, long before they ever cross from one side of the tank to the other.
Precisely. In that scenario, the Knudsen number is extremely small. The standard rule in engineering is that if the Knudsen number is less than or equal to 0.01, the continuum assumption is totally valid.
The macroscopic averages work perfect.
Exactly.
But if we go back to our satellite example in low Earth orbit,
Right. In low Earth orbit, the gas density is so low that a single oxygen molecule might travel meters or even kilometers before colliding with another molecule. If the size of your satellite, your characteristic dimension, is only 2 meters across, the molecule's mean free path is far larger than your system.
so the Knudsen number becomes much greater than 0.01.
Exactly. The holes between the matter are too big relative to the object you're studying. The classical assumptions of pressure and temperature break down entirely.
And you must switch back to the microscopic statistical viewpoint to calculate drag or heat transfer.
You have to.
That is such an elegant way to solve the problem. It's almost like looking at a pointillist painting. If you zoom out far enough, it just looks like a solid color continuum. The Knudsen number just mathematically tells the engineer exactly how far back they need to stand for the illusion to hold up.
That is a wonderful way to visualize it. And once you know you can safely treat your matter as a continuum, you then have to define exactly what part of the universe you are actually going to study.
Here's where it gets really interesting, because we have to actively draw a box around reality. In thermodynamics, you have the system, the surroundings, and the boundary. And if you don't define these correctly right out of the gate, every single calculation you do afterward will be completely wrong.
These definitions are the absolute bedrock of thermodynamic analysis. The system is defined as the specific quantity of matter, or the specific region in space where you are focusing your attention.
And the surroundings is literally everything else, everything external to the system.
Correct. And separating the two is the boundary. The boundary is what defines the limits of the system. What's crucial for engineers to understand is that boundaries are highly adaptable tools.
Like they aren't always physical walls.
Right. They can be real physical walls, like the steel casing of a boiler. Or they can be entirely imaginary lines drawn in space, like the invisible plane across the intake of a jet engine.
Oh, that makes sense. They can also be fixed, like a rigid tank, or moving like the face of a piston moving up and down inside an engine cylinder. I also find it fascinating how we define the thermal properties of these boundaries. In the notes, we classify them as either adiabatic or diathermal. An adiabatic boundary means absolutely no heat transfer can happen across it.
At all.
The thermal resistance is essentially infinity,
Yeah.
whereas a diathermal boundary allows heat to pass right through without resistance.
Exactly. You are defining the strict rules of engagement for the space you are studying, what is allowed to cross the line and what isn't. And by defining these boundaries, you inevitably arrive at a profound mathematical truth. System plus surroundings equals the universe.
That equation is staggering in its simplicity. I mean, when I define my system, say a single cup of hot coffee sitting on my desk, I have simultaneously defined my surroundings as the entire rest of the universe.
You have.
The coffee cup, and literally everything else in existence. And depending on how that boundary behaves, we categorize everything into 3 specific types of systems.
Let's walk through those because how a system interacts with the universe dictates the math we use. First is the closed system, which engineers also refer to as a control mass.
Right. So if I'm an engineer working on a hydraulic press, I'm dealing with a closed system. The hydraulic fluid stays inside the cylinder. No mass crosses the boundary. But energy, in the form of work pushing the piston, crosses the boundary constantly.
Spot on. In a closed system, energy can cross the boundary, but mass cannot. The mass inside the system is fixed.
Right.
The second type is the open system, also known as a control volume.
This is where things like gas turbines, pumps, and jet engines come in. Both mass and energy are allowed to cross the boundary.
Exactly.
My analogy for this would be a boiling pot of water on the stove without a lid. Heat energy is entering from the burner below the boundary, and mass is leaving as steam escapes out the top boundary. You are focusing your attention on a certain fixed volume in space, the pot, and watching matter and energy flow completely through it.
That's a great example. In an open system, we aren't tracking a specific collection of molecules. Instead, we create a control surface, an imaginary boundary around a device, just to track the rates of what flows in and what flows out.
It's a fundamental shift in perspective.
It is. And then we have the third type, the isolated system.
Right. In an isolated system, neither mass nor energy can cross the boundary. The door is locked, the windows are boarded up, and the walls are infinitely thick and perfectly insulated.
If we connect this to the bigger picture, an engineer might attempt to approximate an isolated system by building a perfectly rigid, heavily insulated vacuum flask. But in practical reality, a truly perfect isolated system is nearly impossible to build on Earth.
Right, some heat always escapes eventually.
Exactly. However, there is one ultimate perfect example of an isolated system.
The universe itself.
Yes, because if the universe is defined as absolutely everything that exists, there is no outside for mass or energy to transfer to and nowhere for it to transfer from. It is the ultimate locked box.
Which opens up some massive philosophical questions, but we'll save the existential crisis for the end of our discussion.
Good idea.
Because right now, I want to pivot to how we actually measure the state of the matter inside these systems. How do we quantify the hotness or coldness of something mathematically?
To measure anything in thermodynamics, we first have to understand the concept of equilibrium. A system is in thermodynamic equilibrium if there are no unbalanced potentials, no driving forces within the system that would cause a change.
Right, so everything is stabilized. You can have mechanical equilibrium where pressures are perfectly balanced so nothing moves. You can have chemical equilibrium where no chemical reactions are actively occurring.
Exactly.
And most importantly, for temperature, you have thermal equilibrium.
Correct. Thermal equilibrium means there is no temperature gradient and therefore no heat interaction occurring. And this specific type of equilibrium brings us to one of the most foundational concepts in all of physics, the zeroth law of thermodynamics.
Let's talk about the zeroth law, because on its face, it feels almost painfully obvious. It states, if two bodies are in thermal equilibrium with a third body, then they are in thermal equilibrium with each other.
Yes.
So, if body A is equal to body C, and body B is also equal to body C, then A must be equal to B. Why is this elevated to the status of a foundational law of physics instead of just being like basic associative logic?
What's fascinating here is the history of why it's called the zeroth law. It wasn't actually formalized until well after the first and second laws of thermodynamics were
Wait,
established.
really? They went backwards.
They did. Scientists realized they had been taking this concept completely for granted. They needed a mathematical bedrock to prove that temperature was a rigorously measurable property. Without the zeroth law, the entire concept of empirical temperature measurement basically collapses.
Because without it, we wouldn't be able to calibrate anything.
Exactly. Let's say you are an engineer designing an industrial chemical reactor, and you need to ensure the chemicals inside, let's call that body A, are at the exact same temperature as the cooling fluid in an external jacket, which is body B.
Right.
You cannot mix them together to see if they exchange heat. They are separated by heavy steel walls.
So you introduce body C, a standardized industrial thermocouple.
Precisely. You place the thermocouple inside the reactor until it reaches thermal equilibrium. It gives you a voltage reading that corresponds to a temperature. You then place that identical thermocouple, or an identically calibrated one, into the cooling fluid.
And if it gives you the exact same reading, the zeroth law guarantees, with absolute mathematical certainty, that the reactor and the cooling fluid are in thermal equilibrium with each other, even though they have never interacted.
It essentially validates the entire existence of the thermometer as a viable scientific tool. It proves we can create a universal, standardized temperature scale, like Kelvin or Celsius, that operates independently of the specific materials we are measuring.
It separates the measurement of temperature from just the human sensation of heat. And once we can accurately measure properties like temperature and pressure, we can begin to calculate the behavior of the substances inside our systems.
Exactly. Which leads us directly to the study of gases and the concept of the ideal gas.
So what does this all mean when we are actually running calculations? Engineers use the ideal gas equation. PV equals MRT. Pressure times volume equals mass times the gas constant times temperature.
But this equation relies on the kinetic theory of gases, which makes some, well, massive assumptions.
It does. An ideal gas is a theoretical construct.
Yeah.
To use that beautifully simple equation, we must assume two things. First, that the gas molecules themselves occupy zero physical volume.
Which is impossible.
Right. And second, that there are absolutely no intermolecular, attractive, or repulsive forces between the molecules.
But in the real world, molecules obviously take up physical space, and they exert electromagnetic and gravitational forces on one another. So a real gas isn't going to behave perfectly linearly. No, it won't. But engineers still rely on the ideal gas law constantly, because a real gas will closely approximate an ideal gas under two specific conditions: very low pressure and very high temperature.
That makes perfect logical sense. I mean, if the pressure is very low, the molecules are so far apart from each other that their individual volume becomes mathematically negligible compared to the size of the container.
Exactly.
And if the temperature is very high, the molecules are moving with such intense kinetic energy that any weak intermolecular attractive forces are easily broken. They just zip past each other too fast to stick.
Exactly. When those conditions are met, the error margin of using the ideal gas equation is incredibly small, which prevents engineers from having to solve deeply complex differential equations for everyday problems.
Nobody wants to do that if they don't have to.
Believe me, they don't.
Yeah.
And this brings us to a critical distinction in thermodynamics: the difference between state functions and path functions.
When we calculate properties using the ideal gas law properties like pressure, temperature, and volume, we are calculating state functions. They are also known as point functions, or exact differentials. And their defining characteristic is that they are entirely independent of their past history.
Right. It doesn't matter how the system arrived at its current state. The property simply is what it is.
I always like the mountain climbing analogy for this. Imagine you're standing at a campsite halfway up a mountain. Your current altitude, say 5,000 feet, is a state function. It is a fixed, measurable property of your current location.
Okay.
It does not matter if you hiked straight up a sheer cliff face, or if you took a gentle, winding 3-day trail, or if someone dropped you there from a helicopter. Your altitude is exactly 5,000 feet regardless. It doesn't care about your past history.
That's a perfect visualization. The state function only cares about the coordinates of the present moment.
But the calories you burned, or the muscular effort you expended to reach that campsite, that is work. And work is a path function. If you free climbed the sheer cliff, you did a vastly different amount of thermodynamic work compared to strolling up the gentle winding trail.
The work depends entirely on the specific path you took, even though your final state, your 5,000-foot altitude, is exactly the same.
Right.
And heat is also a path function. How much you sweat, how much heat you transferred to the environment, depends on the trail you walked. And this distinction is vital because thermodynamics, ultimately, is deeply concerned with the paths we choose to take.
Because the path determines how successfully we achieve our grand aim. The path determines how much organized work we successfully extract and how much disorganized heat we inevitably lose to the universe.
Exactly. The state functions simply describe the current condition of our chaotic cats. The path functions describe the actual process, the physical effort of herding them into a marching band.
This has been an incredibly dense but deeply rewarding journey through the architecture of physics. We started with the foundational goal of thermodynamics, organizing chaotic heat into synchronized work. We explored how engineers rely on the macroscopic continuum, carefully validated by the Knudsen number, to avoid the impossible math of tracking individual molecules.
We learned how crucial it is to draw precise boundaries around our systems, defining the rules of engagement for open, closed, and isolated spaces.
We saw how the zeroth law provides the mathematical bedrock for temperature calibration, and how engineers carefully balance the assumptions of the ideal gas law to calculate state functions. Always remembering that while your current state ignores history, the work you do depends entirely on the path you walk.
It is a remarkable framework for understanding the physical world. But as we wrap up, I think we should return to that existential question we tabled earlier.
All right, here we go.
We established that the universe itself is the ultimate, perfect example of an isolated system, a locked box where no mass and no energy can ever enter or leave.
Right. It's entirely self-contained.
We also established that thermodynamics is the science of limits, and its grand aim is to continually convert non-organized heat into organized work. But the second law demands that every single time we try to do that, we pay a chaos tax.
Yeah, we inevitably lose a fraction of that energy back into disorganized, unusable heat.
So if the universe is a closed, isolated box, and we are constantly, inevitably losing organized energy to chaos, what happens when the universe eventually runs out of ways to organize that chaotic energy?
Oh, wow. The concept of ultimate entropy. Eventually, the whistle stops working, the marching band dissolves, and the entire universe just becomes a uniform field of randomly running cats forever.
No more heat transfer, no more work.
Just perfect, chaotic stillness. That is a heavy, beautifully fascinating thought to leave you with today. Keep questioning the physical limits of the world around you, and keep an eye on your marching bands until our next deep dive.